In the summer of 2025, a telescope scanning the sky from Chile picked up a faint moving point of light that shouldn't have been there at all, something moving too fast, on too strange a path to belong to our solar system. Astronomers around the world dropped what they were working on. Within days, the James Webb Space Telescope, humanity's most powerful eye on the universe, was quietly retasked to point directly at it. And when the data came back, scientists studying it found something that didn't match a single known comet ever recorded in the history of astronomy. Not a slightly unusual reading, not a minor deviation from expectations, a chemical signature so far outside anything predicted by existing models that researchers are still, right now, arguing over what it actually means. This is the story of 3I Atlas, the third confirmed visitor from beyond our solar system ever detected by humanity, and the moment James Webb captured something scientists genuinely did not expect to find. To understand why this discovery matters, you first need to understand exactly what kind of object we're actually talking about. Because it isn't a planet, a moon, or an asteroid belonging to our own solar system. It's an interstellar object, a chunk of ice and rock that formed around a completely different star, somewhere else entirely in the galaxy, before being flung out of its home system entirely. Likely by a gravitational interaction with a planet or another passing star, and sent drifting alone through interstellar space for what could be millions, or even billions of years. Humanity has only ever confirmed 3 of these visitors passing through our own solar system. The first, nicknamed Oumuamua, was spotted in 2017, a strange, elongated object that tumbled through our solar system so quickly astronomers barely had time to study it before it was gone again, sparking years of debate about its true nature. The second, Comet Borisov, arrived in 2019, behaving much more like a familiar comet, with a visible tail and a composition roughly in line with what astronomers expected. And then, on July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System, a network of telescopes specifically designed to scan the sky for exactly this kind of object, detected the third confirmed interstellar visitor in recorded human history, an object astronomers designated 3I Atlas. It's worth pausing on Oumuamua for a moment, because the memory of that first interstellar visitor is a big part of why 3I Atlas's arrival triggered such an immediate, urgent scientific response. When Oumuamua tumbled through our solar system back in 2017, astronomers simply weren't prepared. It was detected relatively late in its approach, moved unexpectedly quickly, and displayed a strange, elongated shape, along with a subtle, unexplained acceleration as it left the solar system. A deviation from a purely gravity-driven path that fueled years of scientific debate and no shortage of speculation about what it actually was. By the time researchers fully understood what they were looking at, Oumuamua was already too far away and too faint for the instruments of that era to gather anywhere near the level of detailed chemical data scientists actually wanted. It became less an answered question and more a permanent asterisk in astronomical history, a visitor humanity never got to properly study before it vanished for good. That missed opportunity shaped how the entire astronomical community responded the moment 3I Atlas was confirmed in July 2025. Nobody wanted a repeat of 2017. Telescope time across multiple major observatories, including Webb, was reorganized within days specifically to make sure this second true opportunity wasn't wasted the way the first one arguably was. From the very first days after its discovery, 3I Atlas stood out. Its orbit was confirmed to be sharply hyperbolic, meaning it isn't gravitationally bound to our sun at all, and never will be, tracing a path that will carry it through our solar system exactly once before flinging it back out into interstellar space forever, never to return. Its velocity, measured relative to our solar system, came in at nearly 58 kilometers per second, meaning this object was moving fast enough and on a trajectory strange enough that there was no realistic chance it originated anywhere within our own sun's family of planets. This was, unmistakably, a genuine visitor from somewhere else in the galaxy, and astronomers immediately understood they had an extraordinarily rare, extraordinarily narrow window to study it before it disappeared from view forever. The detection itself is also worth understanding, because it wasn't luck in the way people sometimes imagine when they picture a telescope randomly spotting something extraordinary in the night sky. The Asteroid Terrestrial Impact Last Alert System, or ATLAS, operates a network of automated telescopes spread across multiple locations around the world, systematically scanning the entire visible sky every night, specifically to catch fast-moving, potentially hazardous objects before they get too close to Earth to react to. It was originally built primarily as a planetary defense system, a way of giving humanity advance warning of any asteroid or comet on a genuinely dangerous trajectory. 3I Atlas wasn't a threat. Its path never brought it anywhere near a collision course with Earth, but the same relentless, systematic scanning designed to catch dangerous objects happened to catch this one too. flagging its unusual velocity and hyperbolic trajectory almost immediately, giving astronomers a genuine head start compared to how Oumuamua was discovered 8 years earlier. That urgency is exactly why James Webb Space Telescope was brought in so quickly. Unlike a planet or a star, which will sit patiently in the sky for astronomers to study whenever it's convenient, an interstellar object like 3i Atlas is a one-time event, passing through at tremendous speed, visible for a matter of months before it's gone, permanently, beyond the reach of any telescope humanity currently has. Every single hour of observation time counted. Webb's science team used an instrument called NIR-SPEC, a near-infrared spectrograph capable of splitting the faint light reflecting and radiating off the comet into an extraordinarily detailed rainbow of individual wavelengths, precise enough to identify the specific chemical fingerprint of the gases surrounding its icy nucleus. When astronomers pointed Webb at 3i Atlas in August 2025, while the object was still more than 3 astronomical units from the Sun, well beyond the orbit of Mars, they captured a spectrum that immediately stood out as something unusual. Here's the finding that stopped researchers cold, the specific result that turned this from a routine follow-up observation into genuine front-page astronomy news within the scientific community. The gas cloud surrounding 3i Atlas's nucleus, known as its coma, was overwhelmingly dominated by carbon dioxide, at a ratio compared to water vapor that measured roughly 7.5 to 1. To put that in perspective, most comets studied throughout the history of astronomy, including comets that formed right here in our own solar system, typically show a carbon dioxide to water ratio somewhere between 10 and 50%, water being the dominant, more common ingredient by a wide margin. 3i Atlas flipped that ratio almost entirely, with carbon dioxide outgassing at roughly 7.5 times the rate of water. Researchers directly involved in the analysis described this ratio as among the highest ever observed in any comet studied by humanity, solar system object or otherwise, sitting so far outside the normal statistical trend that scientists measured its deviation at more than 4.5 standard deviations away from what existing models predicted, a level of statistical outlier that, in most fields of science, essentially screams that something about the underlying assumptions needs to be reconsidered entirely. And the surprises didn't stop there. Follow-up observations using a second instrument on Webb, called MIRI, the mid-infrared instrument, equipped with a specialized spectrometer capable of analyzing even longer infrared wavelengths, detected something that had never before been directly confirmed on any interstellar object in history: methane gas, actively venting from 3i Atlas's nucleus as the comet continued its journey inward toward the Sun. Scientists studying the data believe this methane had likely been trapped beneath the object's surface, sealed away in deeper layers of ice for an unimaginable length of time, only beginning to escape once solar heating finally penetrated far enough to reach it. Layered on top of the carbon dioxide and methane, Webb's instruments also picked up water vapor, carbon monoxide, water ice, fine dust particles, and a tentative, still unconfirmed signature of a molecule called carbonyl sulfide, an unusually rich and complex chemical inventory for any comet, let alone one that formed around a completely different star. So why does this chemistry actually matter? Beyond simply being an unusual set of numbers in a research paper, because the specific mixture of ices contained inside a comet's nucleus acts, in a very real sense, as a frozen chemical time capsule, preserving a physical record of the exact conditions present in whatever distant planetary system that comet originally formed in, conditions that have otherwise been completely inaccessible to direct study, since no spacecraft humanity has ever built has traveled to another star system to sample material directly. Every previous piece of information astronomers have gathered about how planets and comets form around other stars has come from indirect methods, watching starlight dim as a planet passes in front of its star, or analyzing the faint glow of dust disks surrounding young stars light years away. 3i's Atlas offered something categorically different, an actual physical sample, drifting directly through our own solar system, close enough for humanity's most sensitive instruments to analyze its chemistry directly, molecule by molecule. And that chemistry is telling scientists something genuinely strange about wherever 3i Atlas came from, information no telescope has ever been able to gather about a planetary system beyond our own, in quite this direct a way before. Researchers analyzing the extraordinarily high carbon dioxide to water ratio have proposed that this object may have originated in a region of its home planetary system, positioned near what astronomers call a carbon dioxide ice line, a specific distance from a young star where temperatures are cold enough for carbon dioxide to freeze solid, but where water ice formation follows a different, less dominant pattern than it does in our own solar system. Alternatively, some researchers believe 3i Atlas may have formed in, or spent a substantial portion of its multi-billion-year journey passing through, an unusually radiation-rich environment, one intense enough to alter the underlying chemistry of its ices in ways that don't match anything commonly observed among comets native to our own solar system. Neither explanation is fully confirmed. Both remain active, competing hypotheses, and part of what makes this discovery so genuinely significant is that scientists are still working through exactly which explanation, if either, correctly accounts for what Webb actually measured. The methane detection deserves its own moment of attention, separate from the carbon dioxide story, because of exactly how difficult a measurement it actually was. Methane is an extremely volatile compound, meaning it turns from ice directly into gas at extraordinarily low temperatures, far lower than water or even carbon dioxide requires. Under normal circumstances, any methane sitting near the surface of a comet's nucleus would have boiled away and escaped into space long before that comet ever got anywhere close to the sun, during the countless millions of years it spent drifting through the deep cold of interstellar space. The fact that Webb's MIRI instrument still detected active methane venting from 3I Atlas strongly suggests that whatever methane the object still contains had been sealed away beneath a protective layer of less volatile material, insulated from the surrounding cold of space for an almost unimaginable length of time, only beginning to escape once solar heating finally worked its way down through that outer shell as the comet approached our sun. Researchers involved in the analysis have pointed out that catching this kind of process actively happening in real time on an object from outside our own solar system offers a genuinely rare opportunity to study how deeply buried volatile ices behave and eventually escape. Physics that had previously only ever been studied using comets native to our own solar system. Consider, for a moment, the sheer improbability of what actually happened here. 3I Atlas likely spent millions, quite possibly billions of years drifting alone through the near absolute emptiness of interstellar space. Following a path shaped by the gravity of countless stars, it silently passed along the way, carrying within it a frozen chemical record of a planetary system that may no longer even exist in its original form, orbiting a star that could be located anywhere across an unimaginably vast stretch of the galaxy. Of all the possible trajectories that solitary ancient object could have taken through the Milky Way, it happened to cross paths with our own solar system at almost exactly the moment in human history when a telescope capable of actually reading its chemical fingerprint happened to be operational and available to study it. A few decades earlier, and this exact object would have drifted through completely unnoticed and unstudied. A few decades later, and it will already be gone, hurtling back out into interstellar space, never to return, its secrets fully sealed away again for good. It's also worth understanding just how quickly this entire scientific process unfolded once the discovery data started coming in, because it doesn't match the slow, cautious pace people sometimes associate with major astronomical findings. The initial NIR-spec observations revealing the extreme carbon dioxide to water ratio were captured, analyzed, and submitted for publication within a matter of weeks after the object was first confirmed. An unusually rapid turnaround, driven directly by the reality that 3I Atlas wasn't going to wait patiently for a leisurely peer review timeline. Researchers across multiple institutions coordinated observation schedules, shared preliminary data, and cross-checked each other's findings at a pace far closer to breaking news coverage than typical academic research, precisely because everyone involved understood there would be no second chance to gather this specific data once the comet moved back out of range. That urgency itself is part of the story. A reminder that even in an era of enormous space telescopes and painstakingly planned observation schedules, the universe still occasionally forces scientists to work fast, react in real time, and publish results, while the opportunity to verify them is still physically available. It's worth being clear about the limits of what's actually been confirmed here, because responsible science reporting demands it, and because the honest version of this story doesn't need any exaggeration to remain genuinely remarkable. Nothing about 3I Atlas's composition suggests anything artificial, engineered, or connected to intelligent life. Its behavior, an icy nucleus outgassing volatile compounds as it approaches the warmth of the sun, is fundamentally consistent with natural cometary activity, just with an unusually extreme, unusually informative chemical mixture driving that activity. Astronomers studying 3I Atlas have been careful, appropriately so, not to overstate the object's uniqueness beyond what the actual data supports, while still being completely honest that its measured chemistry genuinely does sit well outside the range, covered by existing models built entirely from comets native to our own solar system. This is not a story about aliens. It's a story about the universe handing scientists a genuinely rare, genuinely unexpected data point, and about researchers responding to that surprise exactly the way good science is supposed to work, by revising their models rather than forcing the data to fit assumptions that clearly no longer hold. It's worth appreciating just how technologically demanding an achievement like this really is in a field that constantly pushes the very edge of what current instruments can detect. There's also something worth appreciating about the sheer technological achievement required to make a discovery like this possible at all. 3I Atlas, even at its closest and brightest, remained an extraordinarily faint target. A small, distant, fast-moving object, reflecting only a tiny fraction of sunlight back toward Earth. Detecting specific molecules within its coma required Webb's instruments to separate that faint light into individual wavelengths, precise enough to distinguish the unique absorption and emission signatures of carbon dioxide, methane, water, and carbon monoxide from each other, an analytical challenge that simply wasn't achievable with the previous generation of space telescopes. Hubble Space Telescope, still an extraordinarily capable instrument in its own right, wasn't originally designed with the specific infrared sensitivity necessary to pull apart these particular chemical signatures with this level of clarity. It took Webb's combination of a much larger primary mirror, extreme sensitivity in the infrared range, and instruments purpose-built for exactly this kind of spectroscopic analysis to finally make a discovery like this possible, arriving at precisely the right moment in scientific history to catch this specific interstellar visitor passing through. This discovery also matters enormously for what comes next, because 3I Atlas almost certainly won't be the last interstellar object astronomers manage to catch and study. A massive new astronomical survey called the Vera C. Rubin Observatory, which only recently began full operations, is specifically designed to scan huge swaths of the sky repeatedly, night after night, using the largest digital camera ever built for astronomy, dramatically increasing the odds of spotting future interstellar visitors far earlier in their approach than previous surveys ever could. Some researchers have projected that once Rubin reaches full operational capacity, astronomers could realistically expect to detect a new interstellar object passing through our solar system every single year, rather than once every few years, transforming what has so far been an incredibly rare, almost lottery-like event into something closer to a routine, if still exciting, annual observation campaign. Astronomers involved in studying 3I Atlas have already stated that everything learned from this specific object, the chemical signatures Webb detected, the observational techniques refined during this rushed, urgent campaign, will directly inform how the next interstellar visitor gets studied, potentially with even more advanced warning and even more detailed follow-up observations than were possible this time. In other words, 3I Atlas isn't just a singular isolated discovery. It's very likely the opening chapter of an entirely new field of astronomy, one focused specifically on directly sampling material from other star systems, simply by watching patiently for the rare moments when that material happens, to drift close enough for our instruments to actually read it. Right now, 3I Atlas continues moving through our solar system, following its predetermined hyperbolic path, gradually approaching its closest point to the Sun before beginning its long, final journey back out into the emptiness between the stars, this time permanently, never to return to any solar system again, carrying whatever remains of its ancient chemistry back out into the dark it came from. Every additional observation astronomers manage to capture before it disappears adds another piece to a chemical puzzle. Scientists are still actively working to solve, still debating, still refining in real time, using data that quite literally could not have been collected by any instrument that existed before Webb launched. Somewhere out there, orbiting a star humanity has likely never even cataloged, sits the system 3I Atlas originally came from. A planetary environment scientists may now understand slightly better than they did before this object ever wandered into view, thanks to a few frantic weeks of observation, squeezed in before an ancient, icy traveler slipped back out into the dark for good. So when you hear that James Webb just captured something scientists didn't expect, understand exactly what that really means, and understand too that this specific kind of surprise, an object's chemistry deviating sharply from every existing model, is precisely the sort of result that ends up reshaping an entire field, rather than fading quietly into a footnote. Comet science has spent decades building detailed models almost entirely from objects native to our own solar system. A genuinely limited sample size when you consider that our solar system is just one planetary system among the estimated hundreds of billions scattered across the Milky Way alone. 3I Atlas handed researchers their first real physically measured glimpse of how differently the basic chemistry of comet formation might unfold elsewhere, and a single data point that extreme is often enough to force an entire field to start questioning assumptions that had gone largely unchallenged for years. It's not exaggeration, and it's not a story invented to fill a headline. It's real. An object older than our own solar system, carrying frozen chemical secrets from a planetary system light years away, passing directly through our own cosmic neighborhood, at exactly the right moment for humanity's most advanced telescope to catch it, revealing a chemistry so far outside every existing model that scientists are still actively rewriting their understanding of how comets and the planetary systems that birth them actually form across the wider galaxy. If a single interstellar visitor can rewrite the rules this dramatically in just a few months of observation, Imagine what the next one might reveal, especially once new survey telescopes start finding these objects on a far more regular basis than ever before. Subscribe now so you never miss the next real discovery from beyond our solar system.